guess the next presentation is from Bharat Jayaprakash on towards carbon-aware spatial computing.
Okay. Good afternoon, everyone. I am Bharat Jayaprakash from the University of Minnesota, and today I'm going to talk about our paper titled Towards Carbon-Aware Spatial Computing, Challenges and Opportunities. So to start off, it is a well-established fact that we, the scientific community, are actively trying to tackle the challenges of climate change. And we're also well aware of the ill effects of anthropogenic greenhouse gas emissions on our climate. And it is in consideration of that our paper aims to introduce you all to a domain of computing that holds tremendous potential to bolster our control over these carbon emissions. And it is in our pursuit of the quote-unquote net zero carbon future as set forth by the Paris Agreement in 2015 that we present carbon-aware spatial computing as a vital tool. So what is CASC and what are the different facets and subdomains that come under CASC? Well, CASC is a domain of computing that has two primary objectives. Firstly, it tries to reduce the carbon footprint associated with spatial computing itself. Now, for one, this can include these algorithmic models that help in the estimation of carbon footprint of these computation tasks, and it can also include implementing these innovative technologies or innovative strategies that try to reallocate computational resources based on how clean the energy is that is available. For example, job scheduling with the aim of prioritizing cleaner energy for computation, in which you basically decide when and where to run a compute tasks based on how clean the available energy is. Secondly, it holds the potential to reduce carbon footprint from various diverse sectors. For example, carbon-aware site selection is an active problem in spatial computing. And if you were to add the carbon awareness to the site selection problem, you could potentially reduce carbon footprint from a variety of vertical markets, ranging from food and supply chains to transportation, energy, data centers, and so on. So to summarize, CASC has two objectives. It optimizes spatial computing to reduce carbon footprint, and it applies spatial computing techniques in diverse sectors to minimize carbon footprint. So why is CASC important? Well, for one, it offers tremendous untapped opportunities for us to collectively achieve the net zero carbon emissions by 2050, which is set forth by the Paris Agreement. On top of that, emissions from certain sectors, like the transportation sectors and the energy and the electric power sectors, have been reported to contribute majorly to overall annual greenhouse gas emissions. And as of 2021, the transportation system sits at 28%, and electric power system sits at 25%. And CASC offers potential to reduce these sectoral emissions. Another interesting data point that we came across was that the demand for computational capabilities, or high-performance computing, is projected for a multifold growth in the upcoming years, especially because of the forecasted widespread adoption of GPU-intensive technologies like generative AI and blockchain technologies. And we believe that CASC can help. We believe that all of these industries can benefit from the advancement of CASC. So most of the common challenges in the different subdomains of CASC arise from the spatiotemporal nature of emissions data. And when I say emissions data, I'm mostly referring to a data set that contains three major components. It contains the emission source, it contains an estimated emissions value of that source, and then it models all the interdependencies between the emission source and the spatial and temporal coordinates of the emissions. But how does it make it challenging? To understand this, let's consider the energy generation process of power systems or power grids, because that is one of the most common connect between industries, or between pretty much any industry that uses electricity. So first there's the energy source variability, which says that carbon emissions are closely tied to energy carbon intensity. And energy carbon intensity is basically just the amount of carbon dioxide released per unit energy produced, and it is usually calculated in the units of grams of CO2 equivalents per kilowatt hour of energy produced. And this carbon intensity is highly influenced by the local power grid's energy mix. So the question that you can ask is the power grid only using renewable sources, or is it using absolutely no renewable sources, or is it somewhere in between? And the answer to that question is probably going to give you an idea of how carbon intensive that power grid is. Then comes the temporal fluctuations in carbon intensity. Now, carbon intensity is not a static number. It can vary over time, even within a particular power grid. And why does it vary? Because you can have varying access to renewable sources throughout the 24 hours of the day. And that is pretty much what this figure on the right illustrates. So you see two different maps of the United States that represent the carbon intensities of pretty much all the major power grids across the country. And even though most of the shades on the right and the left seem pretty similar to each other, if you average it out and if you look closely, you'll find that most of the shades on the right-hand side, which represent the carbon intensity at 11 a.m., is much more lighter than the shades on the left-hand side, which represent the carbon intensity at 11 p.m., which is nighttime. So this indicates that almost always you'll have power grids that are less carbon intensive during the day than during the night. Then comes the spatial disparities. So the carbon intensity not only varies over time, but it also varies with region, and that is also because of the varying access to renewable energy that the power grids have. And incorporating this highly nonlinear spatial and temporal variations of emissions into the generation process is what makes carbon-aware spatial computing challenging. So to quickly go through the contributions of our article, we introduce CSE, and we offer a structured taxonomy of research areas that can be used by researchers from academia and industry alike to navigate through different open problems. We delve into 4 subdomains where spatial temporal techniques can be applied. And these are the 4 subdomains that we discuss in the paper, out of which 3 of them I'm going to touch base with you guys in this presentation. Moving on to the first subdomain that we discuss in the paper is carbon-aware site selection, which is the process of strategically selecting sites or locations for facilities with the aim of reducing the carbon footprint associated with those facilities. Now, if I were to exemplify it with applications, one of the main applications of such a site selection process is the supply chain industry. And the way to look at it is that every site in a supply chain network, from suppliers to manufacturing units to distribution centers to the immediate customers, they represent a distinct element in a local transportation system. And if we were to relocate some of these sites or add new sites to the network, of course, only after considering the business and monetary implications, we could potentially reduce carbon emissions associated with the transportation inside a supply chain network. Another application is in the data center industry, and evidence from the data center industry shows that the data center vacancy rates are dropping to record lows, and with the expected increase in the use of HPC and computational capabilities, there's immense pressure on companies to establish new data centers or expand existing ones. And some of the ways that companies select sites for their data centers is by considering the monetary cost, or by considering the proximity to hydropower stations, or by prioritizing sites that are in colder climates to reduce cooling costs. Some of the open problems here, especially with the two specific applications that I talked about, is with the supply chain industry, you can consider heavy materials like machinery and construction materials. And we know that transporting these heavy materials are associated with a high carbon cost, because transporting heavy materials requires more fuel than if you were to drive an empty truck. And that increases the total associated carbon footprint. So if we could potentially relocate sites such that we could minimize the specific transportation distances of heavy materials, we could potentially reduce a lot of carbon footprint there. With the data center market, if we are to minimize the carbon footprint associated with computation, what we could do is we could integrate the carbon intensity of the energy produced into the selection process to determine appropriate sites for data centers. The second subdomain that we discuss in the paper is balancing power systems, which mainly involves the management of load of power grids by strategic management of consumer side activities with the aim of reducing the reliance on dirty energy and increasing grid stability. And one of the most prominent applications in this subdomain is the vehicle-to-grid system, or the V2G infrastructure, which is a pretty well-established infrastructure and is also deployed at a very decent scale. The V2G infrastructure is basically a bidirectional charging system for electric vehicles that allows EVs to charge during certain times of the day and discharge during certain times of the day based on certain objective functions. And the V2G infrastructure is versatile in the way that you could use costs to the owner as objective functions, or carbon emissions as objective functions, or you could probably just work with stabilizing the grid. Another similar application is the implementation of a technique called spatial workload migration, which is basically just the shifting of computation tasks or workloads to different locations based on how clean the energy available for use is. So what happens here is that at the minimum, you're working with two different data centers that are connected to two different power grids. And if there's a surge in demand in one of the power grids, what happens is that a large chunk of the workload that is coming to the data center that is connected to that power grid gets shifted over to the other data center. And that is the way such techniques can increase grid stability. Some of the open problems here is, so in seeking to minimize carbon emissions, scheduling algorithms like the spatial workload migration algorithm can come across situations that are called demand bottlenecks, which happens when there's a surge in demand in areas where the carbon intensity is low. So in such situations, the more common practice is to switch on backup power generators that are usually fueled by dirty sources, and that would increase the overall carbon intensity of that power grid. And addressing these bottlenecks is, I think, of utmost importance. Future models, especially predictive models, could solve this problem by incorporating spatial and temporal dependencies of these emissions that can model the interaction between carbon emissions and the grid load, which could help in forecasting grid stability issues better. The final subdomain that we discuss in the paper is that of carbon complexity. Now, in the world of algorithms, or to be more specific, in the world of algorithm analysis, there are two very prominent and ubiquitous metrics that are used for algorithm analysis, and they are the time complexity of the algorithm, which is basically the amount of time it takes for an algorithm to execute with respect to its input size, and then there's the space complexity, which indicates the amount of different types of memory that the algorithm uses. So taking this to the next step, and there was an ACM publication in 2013 in which the authors posed the question, should software be redesigned based on energy optimality? And they went on to subsequently introduce an energy complexity model in the same paper. And in the subsequent years, there were many other energy complexity models that were proposed, most of which lacked the simplicity of the time and space complexity metrics that make them even more popular today. And another thing to note is that the energy usage is one step removed from carbon emissions. And what that means is the energy used by an algorithm is directly, what that means is the carbon emissions associated with an algorithm is directly dependent on the energy used by that algorithm, but it's also dependent on a representative carbon intensity of the energy used by that algorithm, which then subsequently has spatial and temporal dependencies on the emission source. So with these 2 points, we asked ourselves the question, should software be redesigned based on carbon optimality? We have not been able to get an answer to this question because answering such questions would involve a thorough analysis of all the pros and cons of making such a change. And it would also necessitate that we accurately quantify the benefits of making such a change in algorithm design. So in the pursuit of answering this question, we think one of the open problems here is the development of algorithmic definitions for carbon complexity that could standardize assessment within the computing industry. And we think that such a definition could potentially be very helpful, especially for comparative analysis and to determine which algorithm is better based on energy and which is better based on carbon cost. We also think that exploring methods to explicitly integrate location and time aspects of the spatial and temporal dependencies of the emissions into the computational complexity model is what's ultimately going to help us get a more accurate model of the algorithms. Moving on to the societal impact, well, the main societal impact of CASE is that it holds the potential of reducing carbon footprint. And the examples or the applications discussed in the paper kind of exemplify the potential impact that CASE can have. And a point of evidence to support that statement comes from a 2020 study from the Netherlands that report that optimization of vehicle-to-grid systems alone could cut greenhouse gases emissions by to 23.6% and a 13.2 cost reduction. So to conclude, we highlight research opportunities in 4 key problem areas in carbon-aware spatial computing, and we present a hierarchical taxonomy to guide researchers. In the upcoming months, we aim to explore new algorithms and present experimental findings to address the open problems outlined in the paper, and we also try to quantify the benefits of CSC because we think that's really important to understand or to determine if the open problems that we've discussed is actually worth solving or if they're actually pragmatic and reasonable. And we're also trying to determine the economical and political feasibility of all the applications and open problems discussed under CASE, and we're trying to do that by bringing in experts and majors of economy and policy into our discussions. Yeah, that's it from my side. I thank you for listening. If you have any questions,